Alright, so one of the big topics in the course is dealing with just transformations of functions. And you looked a little bit at transformations of quadratics back in grade 10 when we were looking at vertex form. And you saw the whole idea of vertical stretch or vertical compression, a reflection in the x-axis, a horizontal shift and a vertical shift. What we're going to be looking at in 3U is looking at those transformations along with something that we call horizontal stretches and compressions and reflections across the y-axis. Now, before we get into this, you need to have done the transformations investigation using Desmos that was handed out in class. If you haven't done that yet, this will not make much sense, so please make sure you do that first before we go through this. Okay, so assuming you've done that, what you had to do on Desmos there was you were given a piece of a parabola, and then you were told to do different transformations to it. So you were sometimes told to change a value that might make it move up or down. You were sometimes told to do something that might move it left or right. Then you did other things that you can see this is potentially vertical stretch, and then horizontal stretches, compressions, reflections, and so on and so forth. Okay, and once you saw your transformed graph, you had to get an idea of what the transformations were. Okay, now looking at a generic transform function right here. So again, this f here could be any function. In the particular case of your investigation, it was this parabola right here. But I just want you to take a look at and think what a, k, p, and q each do. Okay, let's start with a. So going over here, if I change a, let's say I make a larger. Okay, what you'll see is it gets skinnier and gets a little bit more stretch. What we call that is a vertical stretch. You'll see as a gets smaller, and then more particularly if it gets less than 1 compared to the original one, it gets wider, and we call that a vertical compression. Okay, once a gets negative, you'll see what happens is it has now been reflected across the x-axis. Okay, so a in general gives you a vertical stretch or vertical compression. We would say it's a stretch if the a value is larger than 1, a compression if the value is less than 1, like I see 0.7 here, and if it's negative, we also have a reflection in the x-axis. Okay, so officially it's a vertical stretch compression by a factor of the absolute value of a. I'll talk about what that means in a sec. And if a is negative, it means a reflection in the x-axis. Now, reminder what absolute value means. It means it refers to a distance from 0, but really it means that whatever is inside these absolute value signs can't be negative. If it's negative, it becomes positive. So essentially what that means is, let's say your a was equal to -2. We wouldn't say it was a vertical stretch by a factor of -2 because a negative gives you the reflection. But we'd say it's a vertical stretch by a factor of the absolute value of -2, which is just, in this case, 2. And then the negative would separately tell you it's a reflection in the x-axis. Okay, moving on, let's take a look at k. Let's move this back to normal here. So k, you'll see as I make it larger, it's actually getting narrower. Okay, so what this is actually doing is doing a horizontal compression. Okay, and I see as k gets smaller, it now gets wider and wider and wider. As k gets less than 1, all of a sudden you're starting to see it getting wider, so we call that a horizontal stretch. So picture taking both ends of the graph and pulling them further out to left and right. Okay, as k now moves into being negative, now we see we have a reflection here, and it's been reflected across the y-axis. Okay, now one thing you'll notice here, when I say it's a horizontal stretch compression, it's by a factor of 1 over k. Okay, and the reason for that being, if you take a look at the k value, it's almost like it's a bit counterintuitive, right? You see in here that the x value gets multiplied by k, and you'd think that would mean it's making the x values larger, which would stretch them out. But you see on the actual graph, as k gets larger, it's actually not the case. It's getting compressed in. Okay, so, and you saw that a lot of the times with the transformations that were happening to the x values that seem to be happening in sort of opposite, and hopefully it will cross your mind as what opposite means in math, but we'll get to that in a second. But right now, when you're talking about a horizontal stretch compression, it's by a factor of 1 over whatever that value is, because again, it seems to happen the opposite of what your intuition might be. Okay, last but not least, let's take a look at p and q. So p, if I move it to make it larger, the graph moves to the right. If I make it smaller, it moves to the left, so this is a horizontal shift. Okay, and q, as I change it, to see as I increase it, it moves up, and as I decrease it, it moves down, so we call that a vertical shift or vertical translation. Okay, so let's put those in our notes. Okay, and in general, these are the transformations we're going to be looking at. So ideally, what we're looking at doing here is taking any kind of parent function we've seen so far in this course, right? Be it y equals x squared, y equals root x, absolute value x1 over x, whatever. We're going to do some transformations to it and create some new graphs. Okay, the other thing you're asked to do in that investigation would do something called a mapping rule. Okay, and when we're talking about mapping rules, you may wonder, well, what's a mapping rule actually for? And if you did them back in grade 10, maybe you remember a little bit about it, but if not, that's okay. But what a mapping rule does is it tells you mathematically or algebraically what's happening to an x and y value of a point that's on the graph. So picture, in general, a parent function here. And let's pick a graph that we know pretty well. So let's just say y equals x squared. Okay. On y equals x squared, we have a lot of points, and some of them you know very, very well. Like, for example, you know 0, 0 is a point on y equals x squared. You know 1, 1 is a point on y equals x squared, and so on and so forth. You can do negative 1, 1, 2, 4, negative 2, 4, and so on and so forth. Okay? But all of these points are going to get transformed according to what's happening in the function. So there could be a vertical stretch, vertical compression, reflection, horizontal shift, vertical shift, and what have you. Okay? What that mapping rule does is we can take these points, all of them, plug them into our mapping rule, which we'll have to make up based on our transformations. Okay, and algebraically what that will do is it will then spit out something that we call image points. Which is basically saying, okay, the point 0, 0 underwent all these transformations, where does that point wind up? And what you're going to wind up with is a new point to graph that's going to be on your new curve. And you're going to repeat that process for every single point that is on there. It goes into the mapping rule, gets transformed, and creates an image point. Okay, so as long as you can create the the mapping rule, you can find the points, new points in your graph that you should be able to plot without too much difficulty. So the idea was, how did you create the mapping rule? Okay, so for starters, when you're starting a mapping rule, there's an x and y component to it, right? One involves a transformation that happens to x, and one involves a transformation that happens to y. And you're looking for a pattern here based on what you saw when you're doing your investigation. And one thing you probably know is that anything that happened to the y values, so anything that happened sort of outside that f right here, outside the function, happen the way you'd expect it to. So if you had a +2 on the edge of the graph, the y value shifted up 2. If there was a -3 out in front here, the y value is multiplied by -3. So in terms of the y component of our mapping rule, it's simply going to be taking our y value, our original y value, multiplying by a, and then adding q. So we get a, y, plus q. Okay, as for the x, you may have noticed that everything seemed to happen in opposite. Well, again, what does opposite mean in math? Well, we just looked at last lesson. Opposite means the inverse. So everything that was happening inside the function here seemed to affect the x value of the points in inverse. So how do we determine what that's going to be? Well, let's start by seeing what's happening to x first inside the function. So we start off with x, and the first thing that happens to it is that p is subtracted from it. So we go x minus p, and then we multiply by k. So in terms of our mapping rule, what we're going to have to do is do the inverse. So we're going to start with x. We're going to then first divide by k. So again, for inverse, we're reversing the order and reversing the operation that was done to x to build the equation in the first place. So we start with k, we divide by k, and then we add p. So what does that mean? We're going to take x, divide it by k, and then add p. Okay, and this isn't something you have to memorize, right? Don't memorize this formula right here. You can always figure out the mapping rule from scratch for the x value by just doing what we did here, creating building the function and then creating the inverse of what happened to x. Okay, same thing with y. Look what happened outside the function, see what's happening to y, and build our mapping rule from there. So it's not something you have to memorize, but the idea of creating a mapping rule is going to be something that's going to be very, very important, not only in this course, but in 4U next year. Okay, so let's try another one. So let's take a look at this in a slightly different form. You'll see that in this particular case, here it's k times bracket x minus p, and here it's just kx minus p. So so in this case, there's a different order of what's happening to x. So for our mapping rule here, okay, well, let's start with x here. So let's, again, looking inside the function, what's happening to x. First thing that happens is we multiply by k in this case, and then we subtract p. So for the inverse for my map rule, I'm going to add p first, and then divide by k. So I'm going to get x plus p divided by k. Okay, and you'll see that because the addition of p happens first, when I divide by k, the entire thing gets multiplied by k, not just the p, or not just the x. Okay, for y, what's happening outside that function there, it happens in the order you'd expect, so it's still just going to be ay plus q. Okay, so that's the foundations of how we create mapping rules. Eventually we're going to get into describing the transformations. We want to make sure that when we do the transformations, when we list them, the order reflects our mapping rule. So again, what this mapping rule is, it's an algebraic representation of every transformation that's happening to x. So if I look at what's happening to x here, I see the plus p happens first, so my horizontal shift of p would happen before my horizontal compression by factor 1 over k. Okay, if I'm looking at the y values here, this vertical stretch compression, whatever a is doing, is going to happen before my vertical shift by q. Okay, so we'll see some examples there, but just make sure the order of your transformations comes from the mapping rule and not from the original function. Okay, so in general then, putting this all together, before we do some examples, if you want to graph a transformed function, you're going to have an original function, will likely be a parent function, but could be anything, and just look for some key points that are on there. So we mentioned from using y equals x squared earlier, having the point 0, 0, 1, 1, 2, 4. With root x, it might be something different. You'd have 0, 0, 1, 1, 4, 2. With 2 to the x might have different points. With absolute value of x might have different points. But you're going to need some key points in that original function. Once you have those, you create your mapping rule. Figure how the original function gets transformed into the new function. Okay, those points that you have, those key points, get thrown into the mapping rule to generate your image points, your new points in your new graph. You plot those points, and then you just make sure that your new graph resembles a parent function. And that's just really a check to make sure you haven't made any mistakes, right? If you have an absolute value function and you're graphing a transformed absolute value function, the general shape should still look like the parent function. If it's not, you know you probably made a mistake somewhere. Okay, with all that, now let's actually try and do an example, or 2 or 3 or 4. So in this particular case, what I'm giving you is telling you that f of 8 equals negative 21. Now, hopefully from your function notation, remember that this means that we have a point that when x equals 8, y equals negative 21. That's what that's telling you right there. And given a transformed version of f right here, again, we don't know what f is. It could be any function. We want you to determine the mapping rule, describe the transformations that happen, and then find where the image point of 8, negative 21 goes. Okay, so let's do the first one together. So again, f is just any generic function right here. All we know about is that the point 8, negative 21 is on it. So looking at this from a mapping rule, again, I need a mapping rule component for x and for y. So for x, I'm going to look inside the function and think, okay, inside the function here, what's the first thing that happens to x? Well, I multiply by 4. And then, well, that's it. Nothing else happens. Everything else happens outside the function. So x times 4, so that's it. In reverse, I take x and I reverse the operation, so it's going to be x divided by 4. So the mapping rule for x is going to be x divided by 4. Okay. For y, what's happening outside? Just this multiplication by 3 here. There's no q in this case, so it's just going to be 3y. Okay, so the mapping rule is not too bad in this case. There's a couple transformations happening. It says to describe the transformation. Since I'm here, I'm just going to do the image point right now. So to find the image point, all I'm doing is I'm taking 8, negative 21 and plugging it into this mapping rule for x and y. So I'm going to take x over 4 and replace the x with 8. So it's going to be 8 over 4. Okay, and the 3y, well, the y is negative 21, so I'm going to replace the y with negative 21. And it's just a matter of simplifying. So 8, negative 21, after all these transformations, after all this mapping rule, is going to become 2 and then negative 63. Okay, and last but not least, the transformations. Now remember, the order of transformations should come from the mapping rule, so let's start with x. It doesn't matter whether you go with x or y first. All that matters is that within x or y you have the correct order. So looking at x, the first thing that happens is a division by 4, so that's going to be a horizontal compression by factor 1 over 4. Okay, and looking at y, the only thing that happens here is a multiplication by 3, so it's a vertical stretch by a factor of 3. Again, these two, it doesn't matter the order that's written in because they're affecting different variables, but again, if there's multiple transformations happening to each one, you have to make sure that the order within each variable would be correct. Okay, we'll do the rest in